This is our Autopilot Design 1 Waypoint Tracker project. It is our free project for our mechatronics course here at SDSMT. It was designed by Alex Rens, Preston Cook, and Casey Moeller. Professor Bagusetty was our advisor for this project. Our objectives for this project were to create a starting point for a multi-platform GPS autopilot system. What that means is that we wanted this system to be able to work for an RC car, or a Baja car, or a UAV, or even an AUV. For simplicity's sake, we wanted to demonstrate the autopilot system's functionality by implementing it on an RC car. We also wanted to gain personal experience working with GPS receivers and mechatronics systems. This is the RC car that we used to implement our autopilot system. Some of the main components that came with the car are its speed controller and the main drive motor, as well as the receiver which takes the signal from the Traxxas transmitter. This is the magnetic compass that we added. It gives us the current bearing of the car. This is the GPS that we use to get our current latitude and longitude. This switch toggles between autopilot mode and manual mode. This switch toggles the Arduino on and off. This LED will go from high to low or low to high to indicate that we have achieved one of our waypoints. And this is our custom motor shield with our Arduino Mega. Let's have another look at that. This is our custom Arduino interface board. It was designed and milled by Alex Rens. Here are the header pins which go straight into the Arduino Mega. Here are the special header pins that fit the GPS. And another set of special header pins for the magnetic compass. Over here are the PWM pins which we use to communicate with the servo as well as receive signals from the Traxxas receiver. We currently only use 2 of them, but we have a total of 6 so that this can be easily expanded to other systems. This is the hardware model or brief overview of how the autonomous system works on the RC car. The first thing you can take note of is that the throttle is always controlled by the user. We put this in as a safety feature so that if something goes wrong in autonomous mode, the user can easily bring the RC car to a safe stop. The steering signal, however, depends on whether or not the car is in manual mode or autonomous mode. If the car is in manual mode, the steering signal is passed straight through the Arduino Mega to the steering servo with no changes. If the car is in autonomous mode, the Arduino Mega takes in the GPS and magnetic compass and calculates how much that servo needs to turn to get us in the right direction. This is the flowchart that describes how the autopilot program running on the Arduino works. It covers the major steps and decisions that the program takes as it guides the RC car to the waypoints. Let's have a look at the course that our RC car will be traveling to demonstrate its functionality. We start at this gold star, and then we head towards the McLaurin classroom building. Now there are several sub-waypoints programmed along the way to keep it nice and straight on the sidewalk, or at least hopefully they'll try to do that. Once we hit that major waypoint though, we turn and we head towards the library. Once we achieve that library waypoint, we turn and start heading in the direction of the chemistry building. But we stop at this sidewalk intersection near the quad. Once we hit that intersection, we turn once again and come to this end gold star right outside the arches of the quad. Here's the video of the final run of the RC car. As you can see, it kind of tends to take a sinusoidal path to its waypoints. This is because the steering only has 3 settings: straight, 30 degrees left, and 30 degrees right. So that means it tends to overshoot when we squeeze down on the throttle, and so it has to immediately and quickly correct. It also tends to get stuck in the grass, but since we didn't want to try and redesign any of the mechanical frame, we just sort of kick it along from time to time. And here you can see it approaching that first gold star waypoint, and the LED went from low to high, indicating that it was achieved. And now we'll be heading along that sidewalk, or the grass as you can see, to the other waypoint. Once again, it got stuck, but we have to help it along a little. And now we're approaching the second main waypoint. And as we get a little closer here, you can see that the LED went from high to low, indicating that that waypoint was achieved. Now we'll be heading towards the library. Now we're approaching the third major waypoint. And you can see that the car now turns, and we've achieved that one, and it looks like we're heading to the next one. And now we've achieved that waypoint at that intersection. Now we're heading to the final waypoint right outside the arches of the quad. And now you can see that the steering is kind of locked up, and we're going to take a few victory circles to indicate that we've reached our final waypoint. This is another look at the course, only with some waypoints programmed onto it. The stars represent preset waypoints, and the flags represent captured waypoints that our RC car took as it traveled along the course. As you can see, the stars and flags pretty closely match on the sidewalk. Some future improvements we'd like to work on are smoothing out the steering so that it follows a much straighter path rather than the current sinusoid. We'd also like to obtain a better compass in GPS, as well as investigate some more advanced algorithms for navigation and guidance. We'd also like to be able to wirelessly send waypoints to the Arduino rather than hard-coding them into the program as we do now.